Hey guys, today we will start a new series called Quantum Mechanics. We're gonna take a break from our tensor series and get into some quantum stuff. So our first video on quantum mechanics is gonna be about blackbody radiation. And my plan here is to pretty much build on quantum mechanics from the ground up. And when you're finished with this entire series, you get a good mathematical grasp on quantum mechanics. So let's start. Our first lecture is going to be on blackbody radiation. Now, first we must ask, what's a blackbody? Well, a blackbody is just like, doesn't have to be black actually. It's just an object and the object gets some light. The object absorbs light. Actually not. It doesn't have to be light. The object just absorbs heat, pretty much. So let's just draw some heat waves. The object gets some heat, which gives it energy, right? And then the object starts to lose that heat in the form of light. So let's break this down. What's really happening here is the conservation of energy. Something is gaining heat. Now, what is heat? Heat is just a movement of molecules. So some molecules are bumping into this object here, and they transfer their energy to this object. And this object starts to emit light. And the light is carrying the energy that this object once had, or that it got from those particles bumping into it. So an object gets heat and releases it as light. And that light is called blackbody radiation. Yeah, radiation is just a form of light. It isn't anything spooky, except for some kinds of radiation, like gamma rays and stuff. And this object that gains heat and releases light is called a black body. Though the name is kind of misleading, it does not have to be black. It's just that black objects are the best black bodies, since they actually emit all light, all wavelengths of light, all wavelengths of visible light, that is. So this actually explains why a candle, you have some candle, and if your candle is hot enough, the inside of your candle is going to appear blue. It appears blue because that candle has a lot of energy, right? The candle has a lot of energy, and it's releasing that energy in the form of that blue light. And blue light is actually has relatively high amounts of energy, which is why the center of a candle tends to be blue. This is also why a hot plate. Let's make this a hot plate. When you burn a hot plate, it starts to glow red. What's happening is that it's getting energy and it's releasing the energy in the form of red wavelength. Now, to understand this process more, we need to actually understand the kinds of wavelengths of visible light. So we have red, orange, yellow, green, blue, indigo, and violet. Red has the lowest energy. Violet has the highest energy. This is just the visible spectrum. We can expand the spectrum, and then we get to infrared. Infrared is lower than red. And above violet, we have ultraviolet, UV. It's higher than violet, okay? So there's a bit more to that, but for this video, we're just going to be concerned with those. So here we have lower energy. Here we have higher energy. In lower energy means higher frequency, and higher energy means lower frequency. And we're gonna understand why in the future. So, what do we have here? Well, we get this. If an object is really hot, it wants to release that energy as fast as possible. So if you have an object that's really hot, and it wants to release that energy as fast as possible, what kind of light will it emit? Well, it might emit blue light. Blue light has a pretty decent energy. It has a pretty high energy. So it would emit blue light. If the object gets even hotter, it gets pretty hot. So even hotter, it will start to emit indigo light. It will appear to be indigo in coloration, which has an even smaller frequency. And if the object is even hotter, and it wants to get rid of its energy as fast as possible, then it's going to emit some cool UV light. Actually, no, it's going to emit violet light. And then, even if it gets even more hotter, the object emits UV light, which we cannot actually see. In fact, the sun emits UV light. It's very hot. It emits all kinds of light, but it emits UV light the most. And we cannot see UV light. But some animals, like bees, can. In fact, if you remove your retina, sorry, not retina, I think your iris or retina, you'd be able to see UV light. Like the artist, I forgot his name, Clement, I think was his name. His iris was removed. Like, you have the eye over here, right? And you have the iris over here. If you remove the iris or retina, I can't remember which one it is, then you'd be able to see UV light. The iris prevents you from seeing that UV light because it's pretty high energy and it can damage your eyes. Pretty high energy. That's why we have evolved a retina / iris, whichever one it is. Just a fun part about anatomy, how it connects to physics. So basically, the higher energy in the object, well, it wants to emit the energy fast, so it emits energy at higher rates. The hotter it is, because they can emit it at that rate. So, it turns out that these values are not continuous, and we're going to explain that in the future video. But as of now, we've understand the black body effect, whatever you want to call it. Let's actually put this down in actual mathematics. The intensity of the light that is emitted from a black body is equal to 8 pi times the frequency of that light, frequency squared, over speed of light cubed, times kT. And K is the Boltzmann constant. For our purposes, let's just pretend that A equals 1. We can just change the units up as to where the value is 1. So that's our formula for the intensity of light emitted from a black body. So let's break this down a little bit. T is temperature. C is the speed of light, which is like 3 times 10 to the 8th meters per second, 300 meters per second. It's approximately that. F is the frequency, and then these are just constants, right? And I is the intensity of light, which is like, I believe, energy per area, something like that, power per area, something like that as well. So, let's see what this equation predicts. So here's our equation for intensity of that light that's being emitted from that black body. This is going to be constant. So let's set this as equal to 1. This is also going to be constant. So let's just set this as equal to 1. And this is also a constant. what we're doing here is we're just trying to find out how intensity changes with frequency. Okay, so this is our equation now after setting everything to 1. Yes, we cannot set 8 pi to 1 as pi is a dimensionless value. However, for our purposes, we can just set it to what to 1 just to see how frequency and temperature changes the intensity. So here we have I equals F cubed times T, which means that as your temperature goes up, your intensity also goes up. And as your frequency goes up, your intensity also goes up in turn. And this makes sense. As your frequency goes up, well, there's more intensity. Same thing with temperature. However, when you actually perform this experiment, when you have like intensity here and a frequency here, and you actually perform this experiment of actually like physically observing the intensity and the frequency, the correlation that you get is it starts increasing. Starts increasing, which makes sense. But then it starts to decrease as your frequency goes on. It starts to decrease. The more accurate graph is this one over here. What happens is that your function starts to increase. So increase and then decrease. That's what you actually observe. However, our model that we actually constructed, the I equals F cubed T, predicts that it just goes up as your frequency goes up. Our actual model predicts that the intensity just goes up forever into infinity. It just predicts that it just goes up forever. So that's not necessarily a bad thing. It's just that our model does not agree with reality. It does not agree with what we've actually observed. Our model predicts that as your frequency goes up, your intensity goes up forever. However, what we actually observe is that at a certain point, called the tipping point, your intensity starts to actually go down again. When you think about this a bit more, that kind of makes sense because as your frequency goes up, you don't want it to get infinite energy, right? Because that's impossible. You'd have infinite energy density and stuff. So our calculation does not match. Our model does not match reality. And that's a bad thing. And when your models don't match or do not match reality, or when they're not compatible with reality, then we need a new model to replace the old model. And the new model, the new hip, cool model, is this, where I equals, here's over here, equals 8 pi sorry, this should have been a square. So 8 pi frequency squared over 8 pi frequency squared over c cubed, pretty much the same exact thing, times hf over e to the hf over kt minus 1. I know that's a spoonful, so let's just make this a bit more clean. So if our intensity equals 8 pi f squared over c cubed times hf over e to the hf over kt minus 1. You're probably wondering, first of all, what is this h that we've just introduced here? What is that? What is that h that we just introduced? It shows up here as well. As you can see, it's pretty similar to the classical calculation, where our classical model, let's just write it down. Our classical model says that the intensity equals 8 pi f squared over c cubed kt, which predicts a graph that goes up to infinity. And our new model gives that I equals h pi f squared over c cubed times hf over e to the hf over kt minus 1. Okay, and the graph that this model predicts is actually what we measure in reality, that sort of bell curve that we get, that upside down smiley face. And it actually matches what we actually observe. I'm not going to talk about how we derived this model. I just want to motivate the model a bit and just explain this new model that we get. This new model that we get introduces this term instead of this term over here. We use this instead. As you see, these are identical. This is correct. It's the second term that changes. Now, what's so different about the second term? Well, now we have a new number, h. H is just a constant, like Boltzmann's constant. H equals 6.626 times 10 to the minus 34th. It's a very small number. And E, of course, is Euler's number, 2.7182818284562. Goes on. So we're multiplying it by this term over here. And this is a very small number, and we have f. Now we're dividing it by this exponential minus 1. So what you get after some time, let's just erase this boogaloo. What you get after some time is as your frequency increases, what happens is that your intensity goes up. Your intensity goes up as your frequency starts to increase. But at some certain point, because of this denominator, at a certain point, it goes down again. At some point, this bottom term becomes bigger than this term over here times this term. And this bottom term makes the graph go down again. You can plug in these values for yourself and see and show that it does that. So a better way to actually write this would be 8 pi hf cubed over c cubed times 1 over ehf over kt minus 1. These cubes did not cancel out. That's not how we do algebra. So we get this. As you can see, as frequency goes up, this whole term starts increasing. But at some certain point, this bottom term will outpace this term over here, and the graph will start to go down again. And that actually matches our observation. And it wasn't, I don't think that it was Planck that actually discovered this. I'm sure that's a misconception. It was someone else that discovered this. And Planck used his Planck's constant, which is what h is called, Planck's constant. That was describing something else. So yeah, that's the story of Blackbody Radiation. It's pretty dope. It's pretty cool. And yeah, nothing too surprising here. And in our next video, we will go over the photoelectric effect, which might actually surprise you a little bit. See you guys.